Hi friends, let us discuss the metabolism of ketone bodies. First of all, you may ask me, why do we need ketone bodies? As energy source, we have carbohydrates, we have lipids. Why do we need ketone bodies? The reason is this. Brain does not have a storage form of energy. There is no glycogen reserve in the brain. Okay, glycogen is not available. Why can't brain use something else like free fatty acid? Brain cannot use fatty acids. Why? There are two reasons. Free fatty acids. The word free indicates that the fatty acids are not esterified. Free fatty acids are not free. Free fatty acids are bound to albumin in the blood. Because of this, free fatty acids cannot cross the blood-brain barrier. The second reason is certain enzymes of beta oxidation of fatty acids are absent. They are not expressed in the brain tissue. So because of this, brain cannot use free fatty acids. So we have to give brain something else during starvation. So when will ketogenesis happen? During starvation, right? So during starvation, we are going to partially oxidize the fatty acids. Ketone bodies are nothing but partially oxidized fatty acids. So which organ is going to do this function? That is your liver. Where in liver? Which part of the hepatocytes? That is mitochondria. So mitochondria is the place where beta oxidation of fatty acids happen. So what are ketone bodies? Partially oxidized fatty acids, right? So of course ketogenesis also takes place in the mitochondria. What is the substrate? Again, let me repeat. What are ketone bodies? Partially oxidized fatty acids. What is the product of fatty acid oxidation? That is acetyl CoA. This acetyl CoA is coming from fatty acid oxidation. Okay, let's move ahead. So as I told you, from fatty acids, beta oxidation produces acetyl CoA. This acetyl CoA is converted to ketone bodies. So normally what happens? Acetyl CoA enters TCA cycle, right? So that is what going to happen. TCA cycle also takes place in the mitochondrial matrix. Other than succinate dehydrogenase, all the enzymes of TCA cycle are located in the mitochondrial matrix. Why acetyl CoA enters ketone body synthesis, not TCA cycle? Can you answer me? So what are the conditions in which ketogenesis happen? As I told you, one is prolonged starvation and the other condition is uncontrolled diabetes mellitus. Right. So what happens in prolonged starvation? In prolonged starvation, there is enhanced gluconeogenesis. So because of gluconeogenesis, oxaloacetate is depleted. All the available oxaloacetate will be channeled to the pathway of gluconeogenesis. So lack of oxaloacetate diverts acetyl CoA from TCA cycle to ketogenesis. Let me remind you, oxaloacetate is the catalyst of the TCA cycle. One molecule of oxaloacetate can help in the oxidation of thousands of molecules of acetyl CoA in the TCA cycle, right? So I have already explained this in my previous video. Fat burns in the flame of carbohydrates. So this is a favorite question. This is a favorite question by examiners. In Viva, they ask, fats burn in the flame of carbohydrates justified, right? So which is the flame? The flame is oxaloacetate, right? So oxaloacetate, which is coming from pyruvate, right? And pyruvate is coming from glucose. During starvation, the reverse is going to happen. Oxaloacetate will enter the gluconeogenic pathway. So oxaloacetate is not available. So acetyl CoA cannot go to the TCA cycle. So all the available acetyl CoA comes to this pathway, that is your ketogenesis pathway. So two molecules of acetyl CoA condense to form acetoacetyl CoA. So what is the source of acetyl CoA? Beta oxidation of fatty acids. The product is acetyl CoA, right? So sometimes, see, this is the penultimate step of beta oxidation of fatty acids. Sometimes this acetoacetyl CoA can directly also enter the ketogenesis. So what is the name of the enzyme catalyzing this reaction? Can you guess? This is acetyl CoA acetyl transferase, right? So to acetyl CoA, we are just transferring acetyl group. Why? CoA we are removing. So thio group is removed. So that is why this enzyme is also known as Thiolase. Clear? So sulfur is removed. Thio stands for sulfur. So acetyl CoA acetyl transferase, right? Thiolase. Remember the name of the enzyme? It's important. In the next step, one more acetyl CoA condense with acetoacetyl CoA to form HMG-CoA. Okay. All you have to remember is just HMG-CoA. No need to remember this entire thing. So there are certain students who aim for distinction. Just for them, let me explain. So if you don't aim for distinction, you fast forward this video. Okay. Those who aim for distinction, listen to this. What is this structure? Oxalic acid. What is this structure? Tell me. Malonic acid, right? If you add one more CH2, it will become succinic acid, right? If you add one more, it will become what? The mnemonic is oxalic, malonic, succinic and glutaric. So in oxalic acid, that is, there is no CH2, 0 CH2. In malonic, 1 CH2 group. Succinic, 2 CH2 group. In glutaric, 3 CH2 group. Very simple. Okay, so this is COOH, this is COOH. How many CH2 group are there? 1, 2, 3, right? So this is your glutaric acid, right? And with glutaric acid, what is attached? CoA. So this is glutaryl CoA. So the group to which functional group is attached, that is your alpha carbon, and this is your beta carbon. So this is beta hydroxy, beta methyl, glutaryl CoA. Simple. It's very easy, right? So don't get frightened by the names in biochemistry. The names are very simple. You just have to know the trick. If you know the trick, it's very simple. Okay. No need to remember any of the structures. Okay. The previous anything in the exam, all you have to write in the exam is just write acetyl CoA plus acetyl CoA, acetoacetyl CoA. Just write the enzyme, thiolase. No need to write the structure. Okay. Why am I showing you the structure? Just for you to understand. All right. So what is the name of the enzyme? Can you guess? Is there any ATP involved here? So it is not synthetase. So it is HMG-CoA synthase. Okay, this is not synthetase. This is just synthase. And this enzyme, this step is the rate limiting step. So the rate limiting step of ketogenesis is catalyzed by HMG-CoA synthase. Remember this. Also, there is one more isoenzyme of HMG-CoA synthase. See, this is in the where mitochondrial subcellular location. There is one more HMG-CoA synthase which is also involved in cholesterol synthesis. Okay. The rate limiting step of cholesterol synthesis is catalyzed by HMG-CoA reductase, but there is also HMG-CoA synthase which is cytosolic. Right. So what happens to this HMG-CoA? So in the next step, see in cholesterol synthesis, it is HMG-CoA reductase. But here it is HMG-CoA lyase. The enzyme is HMG-CoA lyase. What is lyase? So in the enzyme classification, there are 7 classes of enzymes. So in that video, I have explained lyase. So what is lyase going to do? It's going to break without using water. So it's going to break without water. HMG-CoA lyase breaks down the 6 carbon HMG-CoA to 4 carbon acetoacetate, and see, I cannot say 2 carbon acetyl CoA because CoA has lot of carbons. So I will say that acetyl CoA, right? Acetyl CoA does not have just 2 carbon. So 4 carbon acetoacetate and 2 carbon acetyl group, which is carried by CoA, right? These are the products of HMG-CoA lyase. So this is the last step. So what happened here? We got a ketone. So ketone body is produced. Look at this ketone, right? So this is the ketone body. This acetyl CoA can enter back to the ketone body synthesis. Since acetoacetate is the first ketone body produced, it is known as primary ketone body. So if there is excess of acetoacetate, this can be converted to acetone. So acetoacetate will be converted to acetone, CH3, C double bond O, CH3, and this can be exhaled out. This is the reason for fruity smell seen in ketosis. So when there is ketosis, the smell of the breath of the patient will be fruity. It is because of the acetone which is coming from acetoacetate. So this reaction is spontaneous reaction. There is no enzyme involved, right? So because acetone is coming from acetoacetate, acetone is known as secondary ketone body. Alright, acetoacetate is the primary ketone body, acetone is secondary ketone body. Also, during fatty acid oxidation, what is going to happen? We are going to remove lot of electrons from the fatty acids, right? So you know there are dehydrogenases, FAD dependent dehydrogenase, NAD dependent dehydrogenase, right? So there are dehydrogenases in beta oxidation. So there will be lot of NADH produced. So in starvation and uncontrolled diabetes mellitus, the NADH NAD ratio will be high. So that means there will be excess NADH compared to NAD plus, right? So what happens? So this NADH will come and reduce acetoacetate to beta hydroxy butyrate. Why do we call this beta hydroxy butyrate? Count the carbons 1, 2, 3, 4. So 4 carbon carboxylic acid, that is butyric acid, right? Acetic acid, propionic acid, butyric acid. The carbon to which the functional group is attached is alpha carbon, and there is hydroxyl group in the beta carbon. So that is why this is beta hydroxy butyrate. So in short, what happens? The ketone group, C double bond O group, is reduced to OH group. Simple, right? So 1H here and 1H here. Simple. So this is a reduction reaction. But the name of the enzyme is beta hydroxybutyrate dehydrogenase. Why? See, the forward reaction is the reduction reaction. The backward reaction is the oxidation reaction. So the enzyme is named in the backward reaction, beta hydroxybutyrate dehydrogenase, the reverse, right? So beta hydroxybutyrate is also a secondary ketone body. Alright. So what are the 3 ketone bodies? The primary ketone body is acetoacetate, beta hydroxybutyrate and acetone. These two are the secondary ketone bodies. If you look carefully, you will notice something. There is no ketone group in beta hydroxybutyrate. So, beta hydroxybutyrate is not a ketone. It is a ketone body, but it is not a ketone. There is no ketone group in beta hydroxybutyrate. Ketone bodies are partially oxidized fatty acids produced by liver. I hope you have understood this statement also. Now we can move ahead. So liver is producing ketone bodies for the use of one we know brain. So brain needs ketone bodies, right, during starvation. What else? Skeletal muscle, cardiac muscle and kidney. So these are the major tissues. Skeletal, cardiac muscle, brain, kidney. These extra hepatic tissue. In the book they will mention all of these as extra hepatic tissues. So that does not mean all the extra hepatic tissues. It's majorly skeletal, cardiac muscle, brain, kidney. They use ketone bodies. Look at the fuel preference of heart. It mainly prefers ketone bodies followed by fatty acids. Glucose is the least preferred fuel for heart. Remember, for cardiac muscle, the majorly preferred is ketone bodies. Alright, so let us look at the reactions involved in the utilization of ketone bodies. So which ketone body we are going to see first? Acetoacetate, beta hydroxybutyrate and acetone. See, this acetone will be exhaled out. So let's ignore the acetone. When there is high NADH-NAD ratio, there will be more beta hydroxybutyrate compared to acetoacetate. So first, we have to convert beta hydroxybutyrate into acetoacetate. The name of the enzyme is same. See, beta hydroxybutyrate dehydrogenase. Here it is the reverse reaction, right? So this enzyme is coming in the ketone body synthesis as well as utilization, right? So from acetoacetate, what we have to remove? We have to remove acetyl CoA. So there is no CoA in acetoacetate. So we have to add a CoA group. So who is going to give CoA group and where is this reaction happening? So this reaction is happening in the mitochondrial matrix only. So this is also happening in mitochondria. In mitochondria, TCA cycle is also happening, right? So in extra hepatic tissues we are talking, not about liver. So in liver, TCA cycle was not happening. That is why acetyl CoA entered the ketone body synthesis. Whereas in extrahepatic tissues, some amount of TCA cycle is happening. Okay. So in TCA cycle, there is succinyl CoA. So the succinyl CoA, it gives the CoA group to acetoacetate and it produces acetoacetyl CoA. Simple. So the reaction is Thioesterase. Remember this, very important. So this is the rate limiting step of ketone body utilization. This thioesterase is absent in liver. So that is why liver cannot utilize ketone bodies. Alright. So to acetoacetate we have added one coenzyme A. We just need to remove acetyl CoA from this. So which is the enzyme? I think you can guess. See here, beta hydroxybutyrate dehydrogenase, it repeated. So some enzyme from ketone body synthesis, that is also going to repeat here. The first enzyme. What is the first enzyme of ketone body synthesis? That is your thiolase. See, thiolase is involved both in ketone body synthesis as well as in utilization. There are so many enzymes of thiolase also, right? So we will discuss this in some other lesson also. So we got, see, thiolase, what is it doing? It is adding CoA here. So in ketone body synthesis, it removed CoA. Here it is adding. So we got 2 molecules of acetyl CoA. So what will be the fate of this acetyl CoA? These 2 acetyl CoA, they will enter the TCA cycle. So you may be asking, how are they entering the TCA cycle? There is absence of oxaloacetate. Guys, that story is for liver. Don't confuse the story of liver and the story of extrahepatic tissues. In extrahepatic tissues, some amount of oxaloacetate is available. That is why acetyl CoA, it enters the TCA cycle. Clear? Very, very simple. See, ketone body synthesis as well as utilization, they are very, very simple. Okay. If it is difficult, just watch the video again. It will be easy. Alright. Let us calculate the energy yield for ketone bodies. NADH will go to electron transport chain. How many ATPs it will give? 2.5 ATPs. If it is 3 in your book, you are reading ancient textbook. Change your book. So 2.5 ATPs. Succinyl CoA to succinate. Because of this reaction, we are not going to get the GTP which is produced in succinate thiokinase reaction of the TCA cycle. That substrate level phosphorylation reaction is not going to happen. So there is loss of 1 GTP. So we can consider is minus 1 GTP or ATP. Right? So minus 1 ATP. What about 2 molecules of acetyl CoA? Complete oxidation of acetyl CoA produces 10 molecules of ATP. So 2 into 10, 20 ATP. So 20, 22.5 minus 1, 21.5 ATP. So one molecule of beta hydroxybutyrate can produce 21.5 ATP. If acetoacetate is coming, so how much it's going to produce? 20 minus 1, that will be 19 ATP. Alright. So 1 molecule of acetoacetate produces 19 ATPs. 1 molecule of beta hydroxybutyrate, it produces 21.5 ATPs. I hope this is easy to understand, right? Alright. Let's move ahead now. So this is something many students confuse. That is why I am emphasizing this fact. The brain can metabolize ketone bodies to meet about 20% of its energy requirements. Remember, 100% of the energy requirement of brain cannot be met by ketone bodies during starvation. The remainder must be supplied by glucose. Is this clear? Only 20% of energy requirement can be met by ketone bodies during prolonged starvation. So brain still need glucose. Why glucose? Because you need oxaloacetate for the acetyl CoA to be utilized. Say ketone bodies are what? They are partially oxidized fatty acids. Ketone bodies are ultimately going to give acetyl CoA only. This acetyl CoA has to enter the TCA cycle. For that you need oxaloacetate, right? Based on our previous discussion, can you name the tissues that cannot utilize ketone bodies? You can also use your logic. Where is ketone body utilization happening? Mitochondria. So name a tissue that does not contain mitochondria. That is your RBC. And previously I told you there is one tissue that lacks the enzyme Thioesterase. So liver lacks Thioesterase. So liver also cannot utilize ketone bodies. So this is another important question they ask. Name the tissues that cannot utilize ketone bodies. So you have to write RBC and liver, and the explanation also you have to write. Try to answer this question. Which of the following reaction is common to both ketogenesis and cholesterol synthesis? What is the answer? Tell me. Formation of HMG-CoA, right? So in both pathways, HMG-CoA is formed. But the reactions are happening in different subcellular compartments. Let us discuss the regulation of ketogenesis. Ketogenesis regulation can be studied at three levels. This is the first level, this is the second level, and this is the third level. Let us discuss one by one. First level is whether free fatty acids are released from the adipose tissue or not. Next level is whether the free fatty acids are entering inside the hepatic mitochondria or not. The third level is whether the acetyl CoA produced from the beta oxidation, it enters the TCA cycle or not. Right? Very simple. What are ketone bodies? These are nothing but partially oxidized fatty acids. So what is the source of fatty acids during starvation? Where are fatty acids stored in the body? Adipose tissues. So adipose tissues contain triacylglycerol. Triacylglycerol has to be broken down, right? You know the hormone glucagon. Glucagon helps in breaking down triacylglycerol. There is an enzyme called hormone sensitive lipase, right? Glucagon will activate hormone sensitive lipase, right? So triacylglycerol will be broken down into diacylglycerol first, and hormone sensitive lipase will act on the diacylglycerol and it releases the free fatty acids. All right. So when glucagon is there, triacylglycerol to free fatty acid conversion will happen more. So glucagon, that is the hormone which is predominant during the fasting state, the hormone which is predominant during the starvation state, right? So glucagon, it activate ketogenesis, right? Whereas insulin, whereas insulin will inhibit this lipolysis. So insulin, it prevents lipolysis, right? Remember this, insulin prevents lipolysis. So this is the first level. Free fatty acids are released from the adipose tissue. Now they have to come to the liver. Why liver? Because liver is the factory in which ketone bodies are produced. So the fatty acids has to enter the mitochondria, right? So which is the rate limiting step of beta oxidation? That is carnitine palmityl transferase 1, CPT1. So this is the rate limiting step. So fatty acids must enter this CPT1, then only they can be oxidized in the mitochondrial matrix. So CPT1 is inhibited by malonyl CoA, right? So malonyl CoA, when malonyl CoA will be produced? When fatty acid synthesis is taking place. When will fatty acid synthesis takes place? In the fed state. So which is the hormone that is predominant in fed state? That is your insulin. That is your what? Insulin. Insulin favors the production of malonyl CoA. So malonyl CoA inhibits CPT1 gateway. So ketone body production is prevented. Alright. Which is the final determinant? The acetyl CoA, which is produced during the fatty acid oxidation, whether it can enter TCA cycle or not, that determines the final step, right? So acetyl CoA, can it go to TCA cycle or not? What is it going to be determined by? By the level of oxaloacetate. So if the oxaloacetate is entering the gluconeogenesis pathway, when will this happen? When there is glucagon excess, right? So glucagon will promote Gluconeogenesis. So when there is excess glucagon, acetyl CoA cannot enter TCA cycle in the liver. So acetyl CoA will go for ketone body production. All right. Very easy, right? So these are the three levels of regulation of ketogenesis. First level is whether free fatty acids are released from the adipose tissue or not. Next level is whether the free fatty acids are entering inside the hepatic mitochondria or not. The third level is whether the acetyl CoA produced from the beta oxidation, it enters the TCA cycle or not. Right? Very simple. Okay. Have you heard of certain fad diets like Atkins diet? Atkins diet is a type of ketogenic diet. Ketogenic diet, as you can see, it contains lot of fatty acids and very, very less carbohydrates. Right? So what is the use of studying this ketogenic diet for a medical student? Tell me, is there any therapeutic use of ketogenic diet? Let me tell you, in Harrison, it's mentioned that ketogenic diet is used for certain refractory cases of seizures. Okay, so certain patients of refractory seizures, we use ketogenic diet. Remember this. Finally, let us learn something about ketoacidosis. What is the meaning of ketoacidosis? Accumulation of keto acids. See, acetoacetic acid, beta hydroxybutyric acid. So these are acids. In the physiological pH, they will lose their proton. So they will exist in the form of acetoacetate and beta hydroxybutyrate. So they will release lot of protons. This is the problem with ketone bodies, right? So ketone bodies, when they are produced more, they are going to lower the blood pH. Acidosis. Okay. So how is this acidosis happening? See this, extreme starvation, uncontrolled diabetes mellitus. What is going to happen? There is more gluconeogenesis in liver, oxaloacetate is used up. So acetyl CoA cannot be used in the TCA cycle in the liver. Also in starvation and diabetes mellitus untreated, what is going to happen? The insulin glucagon ratio will be low, right? So in diabetes mellitus, insulin is less. That means there is unopposed action of glucagon, right? In extreme starvation, what is going to happen? There is more glucagon, right? So insulin glucagon ratio is less. So when they say less insulin glucagon ratio, don't get confused or frightened. It's very simple term. Insulin glucagon ratio is less mean glucagon is more. Okay. So more lipolysis in adipose tissue, more free fatty acids in the blood. So they come to the liver, right? Because insulin glucagon ratio is less. What is going to happen? CPT1 pathway will be open. So they will go to beta oxidation. They will produce acetyl CoA. There is no oxaloacetate. So they cannot enter TCA cycle. There will be ketogenesis. So there is more ketone bodies in the blood and urine. So ketonemia means there is more ketones in blood. So when we say ketosis means ketonemia plus ketonuria, right? So ketosis is equal to ketonemia plus ketonuria. So what are you seeing? Positive Rothera's test. You take 5 ml of urine in a test tube, saturate with ammonium sulfate, right? There is no need to add too much of ammonium sulfate. Just add adequate enough to saturate. Add 0.2 ml of sodium nitroprusside. That is very, very important. That is why it's a nitroprusside based test. After that, gently add 0.5 ml of liquor ammonia along the sides of the test tube, right? So after adding please close the cap of the ammonia containing bottle. Very, very important. So once you do this, you get a purple ring. Okay. So when the examiner comes, what will happen? The entire test tube will be purple in color. So this is what most of the time happens. The entire tube will be purple in color. Why? So that is why I always tell my students, don't add too much of ammonium sulfate. Okay. If you add too much of ammonium sulfate only, the entire tube will become purple in color. So add a little. Initially, the ring will be very, very thin. But when the examiner comes to you, the ring will be thick enough to be seen. Okay. So this is the trick. I have explained all these in a video on urine analysis. So you can watch the video on urine analysis. So urine analysis is the practical. You will have one practical, that is urine analysis, in your MBBS exam. You must watch this video, right? So now tell me, among the ketone bodies, which ketone body will not give a positive Rothras test? Think and let me know. What is that? It is beta hydroxybutyrate. So that is why blood measurement of beta hydroxybutyrate is preferred over urine testing with nitroprusside based assays. Because beta hydroxybutyrate is not a ketone, it does not contain a ketone group. Beta hydroxybutyrate is a secondary alcohol, right? So it won't give Rothera's test. This is very, very important. They will ask you multiple time in vivas. So remember. So that is why in modern medical practice, it is important to perform blood measurement of beta hydroxybutyrate. Okay. Okay. Tell me, why are we measuring beta hydroxybutyrate? Why not acetoacetate? It is because I told you, right? So there is high NADH NAD ratio in uncontrolled diabetes mellitus and starvation. So the predominant ketone body during ketosis is beta hydroxybutyrate. So that is why we are measuring that molecule. Alright. So look at this. Rothera's test may become increasingly positive after treatment of DKA. What is this? Can you understand? Can you interpret this? So there is a person who is suffering from diabetic ketoacidosis. Initially you do Rothera's test was weakly positive. That means, let me explain. In the initial, that is 0. So in the initial, there is more beta hydroxybutyrate, right? Because NADH NAD ratio is very high. There is less acetoacetate, right? That is in the initial step. What happens after treatment? Once you give the treatment, the NADH NAD ratio will start decreasing. So there will be more acetoacetate and less beta hydroxybutyrate during the treatment course. So once the ketosis is reversed within a day or two, the Rothera's test will become negative. Otherwise, compared to day 0 and day 1, there will be increasing in the positiveness of the Rothera's test. This is again very, very important. It's given in Harrison. Okay, so this is from Harrison. This line is from Harrison, right? Defective fatty acid oxidation leads to hypoketotic hypoglycemia. Can you explain why? Conversion of 2 molecules of pyruvate or lactate to 1 molecule of glucose requires how many ATPs? 6 ATPs. When will gluconeogenesis happen? Gluconeogenesis happen when there is no glucose available. So what is the source of ATPs? Not glycolysis. It is fatty acid oxidation. So fatty acid oxidation provides the ATPs and GTPs required for gluconeogenesis. So if fatty acid oxidation is defective, as in CPT1 defect or hypoglycine ingestion, that is unripe ackee fruit ingestion, Jamaican vomiting sickness, even unripe lychee fruit ingestion. So all this will lead to defect in fatty acid oxidation. So there is hypoglycemia. So in these conditions, there will be less ketone bodies. See, normally in hypoglycemia, there will be more ketone bodies. But in these cases, there is less ketone bodies. Why? What are ketone bodies? They are partially oxidized fatty acids. So that is why if fatty acid oxidation is defective, there will be, of course, less ketone bodies. Right? So I hope you have understood the concepts I have explained in this video. So we have learned how ketone bodies are produced, when are they produced, how are they utilized, where are they utilized, and so many clinical conditions we have discussed. If you like this video, please share this with your friends. Thank you for watching. Happy learning.